Estamos acostumados a pensar sites com recursos apenas para o ambiente online. Mas Jake pode mudar nossa opinião durante sua fala na BrasilJS 2016. Desenvolvedor para o Google Chrome e um dos editores da especificação do Service Worker, Jake vai pegar um site online only e transformá-lo em uma web app progressiva offline first, instalável, totalmente resiliente de rede, em frente aos olhares atentos da plateia.
I landed in Brazil yesterday, and a few people were asking me where I'm from, and my standard reply is to say, I am from England. And then people say, well, where in England are you from? And this used to be a difficult question to answer because I'm not from one of the big cities in England. I'm not from somewhere many people have even heard of. But in the past few years, it's actually got a lot easier to describe to people. For instance, I moved to the south, and I'm in a big city, London. This is where all the big buildings are, all the landmarks you're familiar with. That's the Google office there. That's where I work. But that's not where I'm from. I'm from way up in the north of England, in a small little town called Carlisle. Now, in Carlisle, the buildings are not very big. Large parts of the city are in black and white. It's like that in real life. It's really weird. Not a lot of tech going on, so that's one of the reasons I had to move out. But just to hammer the point home, this sort of purple line here is Hadrian's Wall. It's really a thing. This was built by the Romans to keep the wildlings out, or as we call them, the Scottish. So when I moved down south, I actually had to sort of change the accent that I speak with so people could understand me better, because so instead of saying, can I have a pint of beer, please? I would say, can I have a pint of beer, please? And instead of saying, I will avenge the death of Ned Stark, I'd say, I'll have a pint of beer, please. So it's a real honor to be able to open the conference. I mean, it's great to speak first as well, because it means I don't have to watch a load of great talks and worry about my own not being as good. I can set a nice low bar right at the start and then enjoy everyone else's talks. Also, at about 3 p.m., you'll probably find me just lying face down on the floor with jet lag, so don't worry about that. That's entirely normal. But this is the first time I've been to South America, and I really want to hear from you what Chrome and web standards can do better. Because even living in England, I can see that a lot of this stuff can become very San Francisco-centric, because that's where a lot of the work happens, and that's not what I want from the web. So I'm going to be around for the whole conference both days, and definitely the after party. So come and talk to me, tell me what the web's not doing right, what it can do better. Even if I'm hiding in a corner looking socially awkward, that is because I am socially awkward, but I'll get over it. But the thing I wanted to talk about is this. It's a little web app I built called Emojoy, which you can find. Have I got a taskbar at the top there? Let's get rid of that. There it goes. And you can find it at this URL. So when you work in developer relations, like I do, you have to build things from time to time just to prove to yourself and other people that you're still a real developer, that you can still actually write code. And this is what I made. And I turned it into a progressive web app. And if you're looking to do the same kind of thing, the first thing you need to do is to tell the browser how to integrate it with the rest of the operating system and UI. So in the head of the page, you can declare a theme color. And this will sort of change the top color. It will kind of integrate it with the browser. It's a very small thing, but it's a quick win. But you can also add a reference to a manifest. And this is downloaded when it's needed. So the manifest looks like this. It's just a lump of JSON that tells it about icons and background colors. And once you have this, users will be able to add the site to their home screen. And they get the icon that you specified along with the title. But not only that, when they launch it, you get this splash screen as the browser's booting up and your site is getting to first render. So the background color there, and the icon and the text and the color right along the top, that's all taken from the manifest. And once that goes away, the user gets your site, but without the URL bar. So it looks and feels just like a native app. However, this whole illusion comes crashing down when you're offline. I don't know if you've seen that, the offline screen is actually playable. It's a little game with the dinosaur. We had to add an option into Chrome to turn this game off, because in schools, apparently kids were climbing under the desk and ripping out the Ethernet cables from the machines just so they can play this game. So we had to add an option to stop that. But in general, this is a really bad experience. The user has launched our app. They've came to us for content again, and we have failed to such an extent that the browser has to step in and apologize. Well, they don't apologize. They blame the user. You can see this here. You are offline. It's your fault. And this is bad, because if we're competing with native, this is like an operating system failure. It's like when you get that little thing along the bottom that says, abstract Java proxy bean has failed to make a socket or something like that. It's that kind of error. But things do get worse. Offline isn't the worst problem we face. This is, and I call it Li-Fi. This is when your phone says it has connectivity, but it doesn't really. You might experience this sometime today, because we have Wi-Fi at a conference, so you'll get something very similar to this. The Li-Fi experience is just this. So the splash screen goes away when the website gets to first render, but when you have Li-Fi, this never happens. And this is worse than offline, because with offline you get a quick answer. The answer is no, but it's a quick answer. Here the user is just left waiting. And you're forcing the users to stare at this or give up. And with every passing second, the user hates the experience a little more. And I don't know if you've been in this situation, but I'm staring at the white screen or a splash screen, and I'm stuck there, and I think, well, I'm not going to stop now, because I feel like if I close it now, if I waited one more second, it would have appeared. So I'm just sort of left in this limbo of staring at the screen. And so this is why we should avoid treating online and offline as binary states. If we cater for offline and we cater for online separately, this situation goes completely unsolved. And that's why the gold standard is offline first. Offline first solves these problems. I had so much fun making this slide. This is all CSS transforms and mixed blend mode. Mixed blend mode is the best thing we've added in ages. Anyway, so with offline first, we assume offline, and then we do as much as we can with local content, and then we try and go to the network. And the more we get to render without a connection, the more offline first it is, the better it is. So we're thinking of the network as a piece of progressive enhancement, an enhancement that might not be there. And here's how we do it. So to begin with, we register for a service worker. And this isn't some magic manifest format or a config file. It's just JavaScript. Because we figured, why invent some new thing when we have a world full of JavaScript developers and debugging tools? So after the register call, we should wrap it in some kind of feature detect, because, there are older browsers out there that don't support service worker. And this just stops them from hurting themselves and others around them. I should point out, I'm making fun of IE here. Edge is implementing Service Worker. They've got it in their experimental builds. Edge is a really good browser. Anyway, in that script, I'm going to add a listener for the fetch event and just have a debugger statement in there. And so now if I refresh the page, I hit that breakpoint. And it's got this event object here, and that has a request property. And it's telling me about the request for the page itself. We can see the URL there, the headers, the type of request. But I also get one of these events for every request the page makes, like the CSS, the JavaScript, the fonts, the images. I get these events for the avatar images, even though they're on another domain, they're on another origin. So by default, requests go from the page to the network, and there's not a whole lot you can do about it. But once you introduce a service worker, it controls pages and requests go through it. But like other events, like click and submit, you can prevent the default and do your own thing. And that's where things get really interesting. And that's how we can make offline first work. So the first thing I built to make Emoji work offline is I created an application shell, which is just the site without the messages. Just looks like this. So I want to serve this and its CSS and its JavaScript before even thinking about going to the network. Because even if we have a great network connection, serving this from the cache is going to be a whole lot faster. And that's the offline first approach. So we need to cache this ahead of time. Now, the service worker has an event for doing this, install, and this happens the first time the browser discovers this version of the service worker. And it's your opportunity to go and cache everything that you need. So that's what I'm doing here. I'm creating a cache called static v1, and I'm adding the app shell, the CSS, and the JavaScript to it. But these won't be used by default. The service worker doesn't really do anything automatically. You have to tell it what you want. So over in the fetch event, I'm going to start by parsing the URL so I can look at its component parts. And then if the request is to the same origin as the service worker and the path name is just /, I'm going to respond with that shell from the cache. So event.respondWith is my way of saying, hey, I'm going to take control of this. I'm going to do my own thing here. And you pass in a response object or a promise that resolves with a response. And caches.match takes a request or a URL, and it resolves with a response object. So that's done. Also, if we're handling a different path, I'm going to respond with a match in the cache for this request. So if the request is for the CSS or the JavaScript, we'll take it straight from the cache. If it's a different request, then caches.match is going to resolve with undefined. So we need to catch that, and if response is falsy, we'll instead fetch the request from the network. So here we're treating the cache as our primary source for data, and we're falling back to the network. So we're doing that whatever connection the user has. So it's very offline first. So using this pattern, we can fetch the app shell, the JavaScript, and the CSS from the cache. This gives us our first shell render without going to the network. And now we're running JavaScript on the page. So I can display even more content, getting it from like IndexedDB or local storage or something like that. With Emoji, I show the last set of messages that was fetched, the last things the user saw. I just store that in IndexedDB. And I don't just do that for offline users, do it for all users. And then go to the network for updated content and update the page when that arrives. And if that network request fails, that's kind of okay. That's, I'm still displaying content. It's still a good offline experience. And if that network request is slow, that's probably okay too. I can tell the user, hey, we're trying to get data, but it's taking a while. But if the user just came to look at a previous message, then we've given them that, which is great. So to see the benefits of this, I wanted to compare it to the original online-only site with this new offline-first service worker version. So I went to a place called the Comparinator. Fight. So first up, so this is on the left here. This is the online only original, and on the right it's the fancy service worker version. So this is when the device is online. Here we get full content instantly. The one on the left lags behind because it's having to pull everything from the network. But in the offline case, you get instant full content versus a total failure. But the important case here is the Li-Fi one. Here, we get instant full content rather than the white screen of death, And in fact, with our progressive web app here, the experience is the same with every connection type. And that's the offline first goal. The network only matters when it comes to fetching new content. And this is how we compete with native. And we can compete with native. So I wanted to take this silly little web app and compare it with a real professionally built native app. So this is Google Photos. I'm going to launch Google Photos on the left, and I'm going to launch Emoji on the right, and at the same time. And it's so close. In terms of performance, it's really competitive. Emoji is actually 0.2 seconds slower to show content. That's 200 milliseconds, very close. And that's compared to a very well-built native app. But this is starting from cold. This is when the browser isn't in memory at all. If the user had looked at a website recently, and let's face it, the browser is a pretty popular app on people's phones, so it's likely to be in memory, this happens. You end up with a progressive web app beating a native app to content render by almost half a second. And a few people have asked me about instant Android apps, the thing that was mentioned at I.O. And my answer to that is, well, progressive web apps are shippable today. I mean, we saw that in the intro. These Android instant apps, at the moment, it's just a slide deck. None of us have really sort of seen what they can do, how fast they really are, what screens, the permissions the user has to agree to see any of this. Progressive web apps are not Android only. It's one thing that you can ship across thousands of devices, operating systems, and browsers. And it can beat a native app to content render. So Service Worker is shipping in stable versions of Chrome, Firefox, and Opera. And it's been there for well over a year now. It's coming to Microsoft Edge. They've just started landing parts of it in their sort of nightly preview browser. It's a high priority implementation for them. It's under consideration by Apple. They sent some of their senior engineers to the last Service Worker meeting, implementation meeting, which was very encouraging. But we don't have any, they've not promised us they're going to ship it yet, but quietly confident on that. But progressive enhancement means that you can use it today. And if you use Service Worker and your sites suddenly become loads faster in Chrome and Firefox and Opera than they are in Safari, then that gives Apple more reason to implement Service Worker because, they're not in the business of shipping a slow browser. Web developers are really in a position of power here, and that's the power of the extensible web. We want to give you low-level things to play with and to make all your sites faster in the way you want to make them faster, rather than providing you with these high-level abstract APIs like App Cache that don't really work for anything. But anyway, enough about this. Is the stuff that was been possible for a year now. I want to talk a little bit more about stuff that has just shipped. Because I built another app. This is Wiki Offline. Because I wanted to show how a service worker could work for something that was less app-like and more like a traditional website. Without Service Worker, it's all server-rendered, like Wikipedia itself. And my eventual aim was to make all of the articles work offline. But in the first pass, I just wanted to add a Service Worker as a performance enhancement. As before, I built an app shell. So for article pages, it would load this generic shell without the network, and then the page's JavaScript would handle the fetching of the article from the network. So without Service Worker, like any other website, but with Service Worker, I'd re-architected it to be more like a single-page app. So I was very excited about all the work I'd done. I wanted to see how fast it was. So, of course, I went back to the Comparinator. Fight! I wanted to compare the original sort of online-only site with the fancy new Service Worker version. So online-only on the left, Service Worker on the right. And I'm going to load both of them over a throttled connection, or as most people in the world call it, their internet connection. So, go. And I watched this, and I thought, shit. It got slower. It got way slower. Here it is again. So the first render is a bit quicker, but the content, which some people would say is the important part, is over half a second, or it's over 2 seconds slower on 3G. And I had a mild panic about this, because I was like, we've been working on this Service Worker thing for years, and it turns out it's really slow. But it wasn't Service Worker that was the problem. I was using this app shell rather than I was letting JavaScript do the rest, like fetch the content and everything, which is fine if your design already dictates that you do this, but it didn't in this case. I'd re-architected a site into a single-page app. And single-page apps are incredibly slow, and this is why I moan about frameworks all the time. Here's what it takes a website to get to first render. HTML starts downloading, CSS downloads, and now we start rendering content. And we continue to render content as more HTML downloads. We might download JavaScript too, but it should be async. It's not going to disrupt rendering. If you contrast this to a single-page app, the HTML downloads, usually instantly because it's very small, CSS downloads, and then we get our first render. And that's assuming that the JavaScript isn't render blocking, which it normally is, but let's be kind here. Anyway, this is just a basic UI render. And then the JavaScript downloads, it parses, it executes, and then it goes about fetching the content from the network. And once it has all of the content, it adds it to the page, and we get to render. And this is how slow happens. This is why single-page apps can be really slow. I mean, in my case, I didn't lose much time on the downloading of the JavaScript, the downloading of the CSS, because that was all coming from the Service Worker. It was all cached. The problem is at the bottom here. The JavaScript has to download all of the content before showing any of it. The more I think about load time performance, the more I realize that it isn't about the size of the CSS, the size of the JavaScript. It all comes down to being progressive. And this is related to progressive enhancement, but not quite the same. I mean, show them what you've got. Like, all the time you're loading, the user is watching and waiting. Don't make them wait until you've loaded everything before showing them anything. Prioritize the first render, the first interaction. Show the user what you've got as you get it. And this is where I was failing, because I was hoarding content. I was, downloading it all, and once I had it all, I was showing it all. And in retrospect, it seems kind of stupid to be doing this, re-architecting this site into this single-page app model. But for me, this was due to App Cache. This was my App Cache hangover, because App Cache nearly lets you do this page shell pattern, but not quite. But it lets you get so close that you can almost smell it. But just at the last second, it stops you with some horrendous bugs. But once App Cache was out of the way, I was like, really? Is App Cache gone now? Does that mean I can do whatever I want? And I just went straight to the thing that App Cache nearly wouldn't let me have. I went straight back to the page shell model. What I didn't stop to think is the best answer wasn't the one that App Cache nearly let me have. It was the thing it never let me anywhere near. What I wanted was streaming. So this is a sort of simulation of streaming. The numbers are reasonably real. And we can see that with the streaming model, it completes slightly faster than without streaming. So streaming completes without streaming completes. And the reason for that is the processing is happening while it's downloading, which is great. But the biggest win is that some rendering happens ages before the non-streaming version. It's rendering all the time. This is the full HTML spec loading here over a throttled connection. It's a 3 megabyte document. It's still downloading, but it gets on screen after only 20K is received. That's streaming, and this, the web's had this as a benefit for like 10, 20 years. But for a long time, there's been no access to streams in JavaScript, but that is all changing. When we designed the Fetch API alongside the service worker, we wanted a lower level representation of requests and responses, but it was also a good opportunity to create a much better API than XML HTTP request, because it's a horrible, it was an old ActiveX thing that we turned into a web standard. I think next year, XHR turns 18 years old, and I don't want to be using that API when it's old enough to drink. It's bad enough as it is. So when you fetch a URL, you get a promise for a response. And we haven't downloaded the whole thing at this point. This is just when the headers are ready. And now you choose how to interpret the response. So things like response.json, that returns a promise, and you'll get your data out the other side. And this compresses really nicely with ES6 arrow functions, and even nicer with async functions, which are being developed in pretty much all the browsers right now. So here, the keyword await, it pauses the execution of the code until the promise resolves, but it's paused in an async way, so it doesn't block the thread. I think Edge has an experimental version of this. Chrome Canary, I think, is about to. But it produces much easier to read code, so I'm going to be using it in the rest of my examples. If you haven't encountered it before, you can pretend that async code is synchronous. Anyway, you don't have to read the response as JSON. We provided lots of little helpers to read as form data, text, blob, array buffers. And we did this for two reasons. One, it's a nice convenience feature, but also we wanted to ship fetch before streams were ready. So we needed to provide another way of reading the body of the response. But we reserved response.body for the stream. And that's been in Chrome and Opera for around about a year now. And it's also being developed by Firefox, Edge, and even Safari. And here's how you use the stream. Say we wanted to fetch the HTML spec, but read it as a stream. The first we call getReader, and this gives us a lock onto the stream, so it knows that we're the only thing that can read it. And then we call reader.read, and that returns a promise for some data. And this result object here, result.done, is true when there's no data left. Otherwise, result.value is some data. And in this case, that data is a uint8 array of bytes. It's not the whole response, it's just the first part of it. If we want the next part, we call reader.read again, and we keep calling that until result.done is true. So if we wanted to get the length of the response here, we could do this by creating a variable for a total and a variable for the result. Create a loop, and that's just going to read and read and read until result.done is true. And then we can get the value and add its length to the total and log that out. And I can see if I can get that working. live demo. Right, that needs to be bigger, doesn't it? There we go. So let's see if the Wi-Fi is going to work. So this is the same code you saw before. And we should see some logging here. Oh, there it is. This is the HTML spec downloading. So we can see here that the chunks aren't all the same size. They're, I think it's sort of dictated partly by the server, partly by the networking stack of the browser. But what we're actually doing here is inspecting all of these chunks without having to have the whole response in memory. I mean, uncompressed, the whole HTML spec is about, it's well over 8 megabytes. But we're able to look at this without keeping 8 megabytes in memory. A more practical use of this would be to search the HTML spec for a particular string, like the word horse, for example. So we could do this by reading all of the text and then seeing, does the text include horse? But here we're having to allocate 8 megabytes of memory, we're having to download the whole thing and search across it. We can do way better with streams. So instead of fetching all the text, we loop over the stream, just as we were before. Now, one of the problems we face here is result.value is an array of bytes, whereas we want a string to do string matching. And in future, this will be really easy. You'll just be able to pipe the body through a text decoder like that. This would be using a transform stream. Transform streams haven't been standardized on the web yet. So at the moment, you have to do things a little bit more the long way around. So I'm going to get a reader. I'm going to create a new text decoder, which is a standard that's been around for a while, and then loop through again. And here you can see I'm calling decoder.decode and passing in result.value, and that will turn the bytes into a string. And this little option there, stream true, that's really important. I'll show you why it's important. So let's make that bigger again. So this is a simple piece of code here. I've got 3 uint8 arrays, each with 3 bytes in them. I'm creating a decoder, and then for each part, I'm going to try decoding it. And as you can see, the output is garbage, so it's not working at all. But if I add in that stream true option, oh, that's going to be a syntax error. There we go. Wish I could code. That's what happens when you join DevRel. Right, and if I run this, it works. Now, what's happening here is it knows it's a streaming format, so it knows it's going to, it's not necessarily getting the whole picture every time you call it. So we call it with the first 3 bytes, and with stream true, it goes, oh, these first 3 bytes, this is an incomplete, it's part of an emoji, but I know it's not complete. So it gives back an empty string, but it holds onto those 3 bytes. And then next time we call it, we give it another 3 bytes, and it takes that first byte and goes, oh, if I add this to what I've already got, I get the poo emoji. Brilliant, right, I'm going to hold on to that. And then the next 2 bytes, it's like, this is an incomplete emoji again, so it gives us the poo emoji back. And then on the third call, we get the final 3 bytes, and it goes, oh, with those first 2, I can now create the toilet emoji, if I add it to the things I already have, and then byte 33 there is the exclamation mark, so it returns the string back. And this is because emoji are 4 bytes in UTF-8, which is what we're using here. So now we can check each chunk of text and see, does it contain the word horse? And if we find a match, we can cancel the stream. And this is great, because if we find the match in the first, 20K, we can abort the download and save having to download that whole 8 megabytes. But there is a bug in this code, and it's a fairly subtle one. It works fine if our chunks are, my lovely, no match, horse running through the field, there's a match. Great. But what if the chunks were my lovely her, no match, horse running through the field, no match? So we missed the match because neither chunk contains the word horse, the thing we're looking for. So when you're doing this sort of stuff with streams, or filtering streams, searching streams, you need to be able to defend against this bug. And to do this, we keep a buffer that's the size of the thing that we're searching for, -1. So horse, 5 characters, we keep a buffer of 4. So that means we would see my lovely her, no match. And then when we get the next chunk, we would add on the last 4 characters we had, and we match on the word horse. So the code for that is relatively simple, same as before. We've got a result there, but I'm going to keep a buffer. Loop through the stream as before, decode it into the buffer this time. If we find a match, great. If we don't, we reduce the buffer down to the last 4 characters, or whatever the thing we're searching for is -1. So now we're searching a large document, but we're keeping memory usage really, really low, and we can stop the download early. So here's a demo of that on the HTML spec. Let's see if I can clear this. This is a bit more of a complicated example because I'm making it case insensitive, and I'm keeping more of the results around so we can see it. But if I run this against the HTML spec, once again searching for horse, there it goes. And there is a match. There is a match because someone who contributed to the spec is called Tommy Thorson. And he's got horse in his name, which is great. Anyone got any other suggestions for words that might be in the HTML spec, but maybe not? Who? Okay. You're more polite here, actually. When I gave this talk in London, there was silence for a long time because no one wanted to say anything. Then at the back of the room, someone just stood up and pointed at me and went, "Shit." I was like, I hope that's a suggestion and, not just commenting. But I sort of quite scared, just thought, it's not going to be in there. Okay. I ran it. I was like, oh, there's a match. What is there a match on? Oh, yeah, there's Canvas shit region. It's Canvas hit region, but, I'm curious now. Is poo in there? Let's find out. Oh, hang on. Spoofing! There you go. So poo is also in the spec. So, also, I was talking to some developers in India and where connectivity is really poor, and they were doing this. They were sending a blob of JSON down for some search results. And a feature they were asking for is hey, can we detect 3G versus 2G? And the reason is they wanted to send fewer results if it was 2G. Because they wanted a faster render, because it's less to download. But detecting connectivity like that is really unreliable. It's the same, your phone can be saying you're on 4G, but you're actually on Wi-Fi. Very common in India to be on a 4G connection, but with 2G speeds. So it's much better to do something like this, to send something that isn't JSON, but each line of it is JSON, because that becomes a streaming format that's really easy to parse, and you can sort of deal with each result as it arrives. So I got a demo of that as well. And this is very connection dependent on whether this works or not. So if I fetch some JSON, it takes, so about over 1 second. It's always faster on the next attempt because the connection's there. So we're talking about 400 milliseconds. But if we stream it, and sometimes this is no different. It's a little bit different. So we're dealing with it in 300 milliseconds. But if I bring up DevTools and throttle the connection, let's make that bigger as well. So in DevTools, we've got ways of throttling the connection here, so that's what I'm going to do. If I can get the mouse on that 1 pixel. I'm going to throttle it down to regular 2G, and let's see how that changes things. So now if I fetch regular JSON, so this is throttling the connection as well. It's probably going to take far too long. Okay, so it's arriving in about just under 5 seconds. But with the streaming version, we get the first bit of data in 300 milliseconds, and the rest of it's going to take the full 5 seconds. So if you're on a slow connection, being able to stream data like this, it will allow you to get something on the screen a whole lot faster. So you might be wondering how I can use this to speed up my Wikipedia demo. Well, I can't really. It's completely separate. Because although you can use fetch to read a response in little chunks like this, JavaScript has no access to the streaming HTML parser. It might look like here I'm happily adding HTML into an element, but when you do plus equals like this, you're actually getting and setting, so it's more like this. You're asking the browser to take the article element and turn it into HTML text, serialize all of it, and then you're adding on more text and asking it to parse all of that. So the elements at the start of this string get created multiple times, and performance just goes through the floor. It's a real disaster. I'm hoping we can provide an API to actually stream HTML into an element, but it's not there yet. But in Chrome now, and this is something we released only a few weeks ago, you can create your own readable streams. They look like that. That's the API for it. You pass in an object with some methods like start, pull, and cancel. Say we wanted to create a stream of random numbers. So I'm going to create a variable for an interval, and you'll see why in a moment. I'm going to create a stream. And in the start method, which is called straight away, I'm going to set up an interval that pushes onto the controller every second, just a random number. The controller there has other methods like close and cancel. Here I'm also going to add a cancel method. So if the person looking at the stream wants to cancel it, this method will happen and I'll clear the interval. So now this is just like a fetch stream and it can be read in exactly the same way. So if I show a demo of that, here it is. So this is the same code you saw before, and here I'm going to get a reader, read it 3 times, and then cancel it and try and read again. If I try and run that code. Every second we're seeing a number appear, but then it's cancelled and we don't get a 4th number. So this is what we call a push stream, because we're shoving data into the stream every second, whether someone's reading from it or not. So eventually we're going to get into memory problems if no one reads the stream, because all of these numbers are going to be buffered up. An alternative to this is a pull stream. So here we create a pull method, and this is only called when the buffer is not full. So when no one's reading when someone starts reading from it, when someone's pulled values out of it. And in here, I can wait a second and generate a random number. And I don't need a cancel method here because we're only going to be generating numbers when someone is asking for them. So streams can be of anything as well. With fetch, we saw them being uint8 arrays. Here, they're numbers. They can be objects. They can be image elements. They can be anything. The designers of streams spent a lot of time talking to the Node folks, because the Nodes had like 4 different versions of streams, and they're very open about all of the mistakes they've made, so we were able to fix a lot of them here. And one of them was to make sure it was just one stream type, no matter what the kind of object you were passing through it. So you might be wondering how I can use this to speed up my Wikipedia demo. Well, I can't. It's kind of unrelated. Not just using streams on their own anyway, but things get a lot more interesting when they're combined with a service worker. So this already streams. The browser's smart about this. You've passed in a response object from the network. It connects the dots, and it streams. It bypasses the service worker after headers and streams to the page. This also streams. It just streams from disk, from the cache. But in Chrome now, in the very latest version of Chrome, you can also create your own streaming responses. So here I'm going to create a text encoder. And this is the opposite of before. This is something where I can give it a string and it turns it into bytes. Because if I'm creating my own fetch stream, it has to be a uint8 array of bytes that we feed down the wire. And then I'm going to create my own stream that is going to wait a second and then push a paragraph containing a random number. And then I'm going to respond with that. So new response, pass in the stream, and I'm going to set some headers to say that it's HTML content type. And if I load that, this is what happens. We can see the random numbers appearing one by one. But one important detail is that the loader there is spinning, because as far as the browser is concerned, it is just receiving an HTML response very slowly. It's just getting a stream of bytes. You might be wondering how I can use this to speed up my Wikipedia demo. Well, I can. This is the bit that makes the difference. Because in that last example, we were piping content straight into the browser's streaming HTML parser. And that's the key to it all. This is what AppCache wouldn't let us do. Instead of turning a perfectly capable server-rendered site into a single-page app, I can use Service Worker more like I would my server. So what I did for the Wiki Offline is I fetched the header of the page, the footer of the page, and the body as 3 separate requests. The header and the footer coming from the cache, and the body is coming from the network unless the network fails, and then it gets an error page from the cache. And then I combine those 3 streams together into one stream. Combine is a function I wrote. It's only a few lines, but I'm not going to show it. It creates a single stream that is the header, and then the body, and then the footer. And then I can create a new response using that combined stream. And this is like what we do on the server. We've got text content on the page. We'd be getting some of it from a template, some of it from a database, maybe some of it from a web service, but we're sending out one response. And this is the same that we're doing here, just from our service worker. Treating your service worker like a server maps really well to things like blogs and Wikipedia. And to see the result of this, for one last time, we go to the Comparinator. Fight! Here's how it compares. So on the left, I've got the app shell render, and on the right, I've got the streaming service worker, both over 3G. And you see the difference in performance is huge. But we'd already seen that the app shell was slower than just standard network. So let's compare it to the original server render. Here they go. So we get the benefit of that cached first render, that just the bar across the top, which happens without the network. And this allows the network stuff to be happening in parallel, and it gets on screen quicker because there's less to fetch, because it's just the middle body segment. I'll play it again. So you can see bang, bang, it's on screen way earlier than the plain old network version, even though the content is still coming from the same network connection. So I'm really excited about streams. But that doesn't mean that the app shell model is bad. It depends on what you're building. I use the app shell model in Emojoy, and it works really well. And the result was a PWA that loads faster than a native app. But a streaming solution will be faster and easier for you if you use server rendering. Switching to an app shell model from server rendering loses you performance, so avoid that. If you already use a single-page app, then you're already suffering the performance problems of that, so it's fine to use a page shell in your service worker. I'd also consider streams if the initial content may come from the network, because you want to be able to pipe that through. Also consider streams if a partial content render is valuable to you, which it is with Wikipedia, because some of the Wikipedia articles are really long, but it's valuable if we can just get the first few paragraphs down when they have been downloaded. So this has landed in Chrome in the latest version. It's something that I know with Facebook, they're developing a progressive web app, and they're going to use streams because they found it to be the fastest solution. So it's something I really recommend checking out. If you want to know more about it, I've written an article about them because I was really excited about it, and I do some sillier things here, like transcode an MPEG to a GIF on the fly, which I don't think is particularly useful, but it's something that streams allows you to do. But also stuff like this. Let's say here I'm reading the Wikipedia page for cloud computing. But using a transform stream to replace every instance of the word cloud with but, which makes it a much easier to read article, I think. There's one of my favorite sentences in here, which is, I think it's about Oracle. Where is it? I could spell. There it is, yeah. In 2012, Oracle announced the Oracle but. While aspects of the Oracle but are still in development, this but offering is, I love that phrase, a but offering. That's great. But using a transform stream for this means I'm not having to download the whole thing and then do a find and replace and then serve it. I can do the find and replace on the fly. So Service Worker lets us create great user experiences. This is Bruce Lawson's logo for the Service Worker because we don't have a better one right now. I kind of like it because if you stare at it, it looks like the colors are changing. The colors are changing. It's got a CSS filter on it. But it kind of makes me feel drunk. I kind of like it. I realize I've shown a lot of code today, and I've gone through a lot of it at lightning speed, but there is a free Udacity course, which I developed along with some colleagues. It's fully interactive, where you take an online-only website to full offline first. It covers the app shell model, and it covers IndexedDB. Tries to make that a little bit easier to understand. Don't worry too much about remembering the URL. Just Google for Udacity offline, and you'll find it. And with that, thank you very much. It's been a pleasure. Cheers.